Hey everyone, I'm Mike Connors, and this is How It Ticks, a podcast about the systems, stories, and ideas that shape life in Switzerland. My guest today is Kathrin Altwegg, astrophysicist and professor emerita at the University of Bern, and one of the key figures behind one of Europe's most ambitious space missions. Kathrin spent much of her career leading Switzerland's contribution to space science as the head of the ROSINA project, one of the main instruments on the Rosetta mission, the first spacecraft to ever orbit and land on a comet. In this episode, we talk about Kathrin's journey into science, why Switzerland, despite its small size, plays such an important role in space research, and what it means to lead a mission that spans almost 20 years and billions of kilometers. We break down the goals and discoveries of the Rosetta mission, what it taught us about the origins of the solar system, and why the discovery of an amino acid on a comet 7 billion kilometers away from Earth is so significant. Kathrin also reflects on what it felt like when the mission came to an end, and what she hopes the next generation of space science will uncover. Now, here is my conversation with Kathrin Altwegg. What first sparked your interest in space exploration? My understanding is that wasn't where you originally started when it comes to studying.
No, I started out with physics. So I did solid state physics in my PhD work in Basel. And then I moved to New York. I did physical chemistry there. And then ended up in space research by chance.
What was the chance?
Well, I met my now husband during my PhD work. We were working on very similar topics, organic molecular crystals. He had to show me how to make crystals, and that's how we fell in love.
Romantic.
Yeah, well, you know, it was a small room in the cellar, and so you had to be close together.
Comfortable in each other's personal space.
Yeah. And so we were able to have two positions in New York at the New York University in two different groups. But then we were looking for two jobs, which were geographically close in Switzerland. And that was not easy at that time. And so there were two jobs in Bern, one at the university in space research, and the other one in telecommunication, a company for telecommunication. And the company didn't want a woman. So it was easy who had to take which job.
Interesting. So you really landed space research because it was the only job at the time that would take you in Switzerland.
And was close to the job of my husband, yes.
And sure. Right. How was the space exploration scene in Switzerland at that time?
Well, Bern already was quite heavily involved in space exploration due to Professor Johannes Geiss. He was involved in Apollo 11. So Bern flew the only non-American instrument on Apollo 11. And that was a solar wind sail, an experiment to measure the solar wind on the moon. That was a simple experiment. You know, just some aluminum foil. The astronauts took it to the moon, put it on the moon, and because you don't have an atmosphere and you don't have a magnetic field on the moon, particles from the sun can penetrate directly on the surface of the moon, which is not possible at Earth, because we have a magnetic field, they are turned around, and we also have an atmosphere, so remaining particles just react with the atmosphere before they reach the surface of the Earth. And so then, in the end, the astronauts took the foil again and brought it back to Bern. After that, Bern was involved in the first European spacecraft, that was CEOS. That was a spacecraft around the Earth, measuring the interaction between solar wind and the Earth's magnetosphere. By that time, ESA, the European Space Agency, was formed, and actually Switzerland is a founding member of ESA. We are not part of EU, but we are a founding member of ESA.
All of the research that comes out of University of Bern, how does that translate into the courses which students go and study? I'm assuming that when you have this relationship with NASA, you have very interesting people. Does that also correlate to interest in the area of people wanting to go and study?
If you want to go into space research, you start with physics. So that's a normal physics course, at least up to the bachelor. After that, you can try to do the master thesis in space research already. And we have several groups, and we always have students doing master thesis in the field. Of course, we also give courses then in this field. So about comets, about the solar system, about planets, about planetary atmospheres, and so on.
Do you think when there's huge events like putting up the James Webb Telescope, or when you have some accomplishments from SpaceX, these big events which make the news, do you think things like that spark people's interest in exploring space?
Well, James Webb, yes. SpaceX, probably no. You know that SpaceX is normally not science.
What do you mean?
SpaceX is not science. They don't do science. They do commerce. It's all about Starlink.
But what about the innovative rockets?
Well, rockets is not space science. It's space technology.
More technology.
And they do that at ETH. But in Bern, we really do science, real science. We build instruments to do science, but we don't build spacecraft, we don't build rockets.
Do you think Switzerland's contribution to space science is a big contribution within Europe?
Yes, yes, definitely. As I said, we are a founding member of ESA, and we were involved in most ESA missions. We were involved in many NASA missions, also in Japanese missions, JAXA, even in the good old times in Russian missions, and in India missions. So we are involved globally in space missions, building hardware and flying them.
Is that because the Swiss have a skill set in an area of expertise which the rest of the world respects and needs?
Yes, I think so, especially the precision mechanics.
Mechanics.
From watches, building watches, you know.
Of course.
In space, there are a few requirements. You have to build very lightweight, because each gram costs to launch. So if you apply for an instrument, the most important number is the kilograms. And the second most important number is the power. And the third most important number is the data rate. So, and you have to minimize them and still do a very good experiment. And I think that's one of our plus points. We can build very good instruments because we can machine them very precisely.
Precision engineering definitely is the branding of Switzerland, that's for sure.
Yes, exactly.
Yeah.
Exactly.
Now, I'd love to talk to you about the ROSINA project. But before I get into that, I wanted to ask you, I know you are quite heavily involved in promoting women in space research and women in STEM. What was it like back when you moved, when there were so few options to the point where some weren't even available to you?
You know, I was the only woman in my class during my physics, but then I did my PhD with a woman professor, Professor Jocker from Basel. And that helped a lot, because for me that was a lot of inspiration. I knew that, after that I knew that women can succeed in science, in physics. And then coming to Bern, Well, also in New York, I had very good mentors. In New York, I had a very good professor. And Professor Geis was excellent for as mentor. And then I had Professor Bautiger. They really believed in me, which is very important. So the problems probably came much later during the Rosetta mission when we were successful.
When you were successful?
Yes.
That's interesting.
Yes.
Well, maybe let's start with the Rosetta project then. If it was difficult as a woman, how did you land the role of was it the head of the ROSINA project?
Yes. Well, when I started in 82, I actually started first with an experiment for the higher atmosphere, the empty instrument. But Bern was then involved in Giotto to Comet Halley. That was a European mission, a very fast mission. So it was decided in 80 and the launch was in 85, which is very fast to build all the instruments and the spacecraft and everything. And it was actually also the first time that Europe did a deep space mission. The Americans were involved first, but then they said they didn't have the money, and anyhow, Europe is not able to do such a mission. That's what they said. And then Europe showed them that. But it was a very stressful time. And so I was moved from the higher atmosphere of the Earth to this instrument, Giotto, and I was responsible for the software. And at that time, in 82, software was no laptop. We had a PTP-11, and so you had to understand something about the hardware, and you had to do Fortran programming. But the good thing is I learned that while I was in the US, because in this physical chemistry lab, I also had a PTP-11 with Fortran. So I had to be there for all tests because they needed this PTP-11 to work with the instrument. And I also had to go to Bristol because that's where they built the spacecraft. They had to go to Toulouse. That's where they tested the spacecraft, to ESA in Noordwijk, Netherlands. That was ESA where they put everything together. So I was always there. So I really got a very good introduction in space missions because I was there from the first point up to almost launch. I was then also in French Guiana. The problem was I was pregnant at that time. My doctor said I shouldn't stay there long because of malaria. So I missed the launch, but all the rest
Must be devastating.
So that was for me a very good introduction. And then I had my first baby. So I reduced my workload. I had my second baby 2 years later, almost 2 years later. I reduced still further. But Professor Balsiger was really supportive in this. I could work part-time and still be involved in, that was then, the mission was very fast, we flew 9 months. And the actual mission was only a few hours because it was a flyby at the Comet. And we flew with 68 kilometers per second. So that was
try to wrap my head around that.
Yeah, it's 68 times the speed of a bullet. That was the first Comet mission.
One.
And then we found out that comets are really very interesting, but you have to have better instruments.
What are you looking for? What problems are you trying to solve? Is it just understanding the world better, or is there specific problems in mind you're hoping to solve when looking at comets?
comets are the best preserved material from the early days of the solar system. So if we understand comets, if we know what they are made of, we can extrapolate backwards. So these molecules, whatever we find, they are older than the solar system. And that means they exist in the universe. And then you can extrapolate or think about how probable it is that there is life elsewhere.
How do you know how old it is? How do you know that it's beyond the age of the, like, this might seem silly, but I just can't understand.
Yeah, let me start again. It's if you build a solar system, you start with a dark molecular cloud. That's a cloud consisting of dust and gas. And this cloud collapses, it gets dense, and in this cloud, the first thing you form are planetesimals, tiny bodies, a few kilometers. And then some of them grow to become a star or planets, and a lot of them remain small and stay far from the star. And these are the comets. So these were really the first planetesimals in our solar system. And they got their material. There is no other possibility. The material was already there in this dark cloud. Because they are way too far from the sun. There is no chemistry ongoing in a comet. It's 30 Kelvin, which is minus 240 degrees Celsius. You don't have chemistry there. So the molecules are older than the solar system, and it's the material our solar system was built from.
Interesting.
Yeah.
Now, the Rosetta project. I've tried to summarize it myself. You tell me if I get this right. And also, I'm probably going to get the name of the comet wrong when I try to pronounce it.
Yeah, that's okay.
So Rosetta was a European Space Agency mission launched in 2004 with the goal of studying Comet 67P Churyumov. Can you step in for the name?
Churyumov-Gerasimenko.
Thank you. Let's just maybe refer to it as 67P from now on to save the embarrassment of me. It was the first ever spacecraft to orbit a comet, carrying a small lander called the Philae, which made the first ever soft landing on a comet surface in 2014. The mission lasted 12 years, covered more than 7 billion kilometers, and provided groundbreaking insights into the early solar system, including the discovery of organic molecules like glycine.
Yeah, very good.
Thank you. I'm not going to lie, ChatGPT helped me with the phrasing towards the end, as you could probably imagine.
Yeah.
How do you even begin to plan something that you know takes more than 10 years to execute?
So the first step is that you have to convince ESA and politicians that this is the right thing to do, to make a mission to a comet and orbit the comet. And that was still Professor Geis with colleagues from all over Europe who did this job. So they convinced first ESA and then the politicians that this mission is better than other missions for Mars or whatever. You know, there is always a lot of ideas in scientists' head, and you cannot do everything. But they convinced ESA that this is the right thing to do. And then the next step is that this is an announcement to the scientific community, and you can propose instruments to be flown on this mission. That was in 1996. And my former boss, Professor Balsiger, he was a very clever man. He involved everybody in the science community working on mass spectrometers in our team. So we had no competition.
That's handy.
At least that's what they say. So we actually got got a yes from ESA that we could build it. And we got 21 kilograms.
You get a designated amount of weight you're allowed to provide them.
ESA decides. So we had a mass in our proposal, which was 30 kilograms. And they said, no, you don't get the 30, you get only 21. Because we had 2 mass spectrometers and a pressure sensor in our proposal. And they said, 1 mass spectrometer is enough. And then again, my boss, I went with him to ESA, and my boss told ESA, if you give us only 21 kilograms, I will not do it. And because we had no competition, ESA had
Sneaky, all right.
Yeah. ESA had to give us 30 kilograms, and in the end, it was actually 35 kilograms.
Oh, right.
And we did 2 mass spectrometers. You know, if you have a mission for 12 years and the mass spectrometer was really, I claim, the most important instrument, you need redundancy. They were not the same. So one could measure faster, but less precise. The other one could measure very precise, but it took time to do it. And we used both in the end. So that was good.
And so you said 1996, that's still 8 years before it actually left.
Yes. So once you get the project, then you need funding. And the funding is done in Switzerland by Prodex. That's a program called Prodex. It's money which the Confederation pays to ESA to build instruments in Switzerland. So the money goes to ESA and then comes back. And if you get the money, 50% has to go into Swiss industry. So you're forced to cooperate with Swiss industry, which is good. That's okay. That's a win-win situation for everybody. So we got the money. We also had co-investigators from all over the world. So we have people from Germany, from France, from Belgium, and from the US. And if you have co-investigators, in principle, everybody pays his own hardware. So we got electronics from the US, NASA paid for it. We got electronics from Germany, DLR paid for it, and so on.
Okay, so you get electronics from everywhere, and it would be the Swiss industry that would actually assemble it.
Swiss industry and the University of Bern.
And the University of Bern.
Yes. Swiss industry actually made the housing, the precision mechanics, the magnet, the electrostatic analyzer, whatever we needed. And then the put together we did together with industry, especially integrating the electronics from our colleagues. And what the colleagues get is for providing hardware is then they get data. They get all the data we get with this instrument. So the currency is data.
Interesting. And so once all of your co-creators are there, you've been supplied everything, does that take us all the way up to 2004, or is there still other steps before?
No. And then you really test it. You look if it does what you think it has to do, but you also put it through temperature cycles between minus 100 and plus 150 degrees. You shake it, you do everything with it.
How do you simulate traveling very quickly through space? I guess you have different testing methods to be able to get as close as you can.
Yeah, the traveling is not the problem. Once you survive the launch, it's very quiet, you know. Not much happens up there. I always say there is no red light. There's no police up there. You just travel. You also don't need much energy. You just travel. It's the speed you got from your rocket. But the what you have to survive is the launch, the vibration of the launch, and then you have to survive the different temperature regimes you have out there. If you're close to the Earth or close to the sun, it gets pretty warm. If you're far out, almost at Jupiter, it gets pretty cold.
What percentage of success did you give it before you started?
It had to work. There was no option of not working. But of course, I think the biggest risk is the launch, which could have gone wrong. It was an Ariane 5. You never know. Then the solar panels of the spacecraft, which would not come working. That had happened before. You know, they are folded together and then they have to go outward, and that's a critical maneuver.
I watched there's a documentary on Netflix about the installation or the process to get the James Webb Telescope into space, and they kept saying there was 350 single points of failure that could happen, which would.
But the James Webb is a very, very complicated, and it's only one instrument. In principle, it's one telescope with different receptors, but that was an extremely difficult thing to install. Rosetta was not that difficult.
Well, with Rosetta, given that it's such a long period of time, and there are, I guess, different points in where it can be successful. I was also reading that the huge next challenge was actually getting Rosetta to land on the comet.
The Philae.
The Philae. Thank you. So I guess the question is, do you have a very clear list of what you hope to achieve before you consider this to be a success? Like, if it didn't land, is it still a successful mission?
Yes. That's important to note. Philae was looked at just as one experiment, like ROSINA. It was not Rosetta. Philae was just one experiment, and it was a high-risk experiment. We knew that. Because we had no idea about the surface of the comet. You don't know if it's soft. I remember there was a meeting in the early days near Munich in winter, and they brought the mock-up of the Philae lander, the Germans, and they put it into the snow. It was powdery snow, and it just sank. You didn't see it anymore, and so this could have happened on the comet.
Interesting, really? Right.
We didn't know if it's powdery snow, if it's a very hard surface. So we knew that it's actually a very risky.
There's really a possibility. I mean, it's just, I guess my influence of what comets are made of is based on Hollywood movies. And of course, they're always hard in Hollywood movies, but there's a real possibility that the surface is just soft.
Right. Half of a comet is water ice and CO2 ice, dry ice. So it's really, it's like a snowball, a dirty snowball.
A dirty snowball.
Yes. And 75% of the comet is void.
What do you mean?
So
it's empty.
Very porous. It's very porous. The comet, it looked like a duck.
I remember reading that, actually, yeah.
It actually could have swum on the Lake of Thun or Lake of Sea. Because the density was only half of the density of water.
And what was the size of it?
4 kilometers.
4 kilometers from the longest ever.
Yeah.
And so so before you arrive at the comet, you got 10 years of traveling through space. What are you doing in that 10-year period? You just go back and work on something else? Is there active work?
No, we were actually busy with Rosetta. Once a year, we had tests with the spacecraft and the instrument, so we could switch it on, test it. We were still working on software because you can upload new software, and we didn't have enough time before launch. And we built actually 2 models which could fly, a flight spare. And in the end, we flew the flight spare to the Comet, and the flight model was still in Bern. And then we calibrated the flight model on a mock-up Comet, which we have in the lab.
You said that you can turn the Rosetta on once in a while, you can gather data. I struggle to understand if it's billions of kilometers away, what kind of control do you have?
Good question. Well, it depended where the spacecraft was. So the first switch on, it was still relatively close to the Earth.
Just a couple of 100 million kilometers?
You had to wait a few minutes to get an answer. But when we were far out, before going into hibernation, it took 3/4 of an hour. One way, so 1.5 hours. You sent the command, and then you could go for dinner.
And it's just radio waves sending it.
Yeah, it goes with speed of light,
yeah,
which is not that fast.
And you need direct line of sight to where Rosetta is to be able to communicate with it?
Yes. But the antenna, we used several antennas. The main one was in Australia, because the southern hemisphere was better for this line of sight. But of course, then you have connection maximum of 8 hours per day, because the Earth turns around and then you lose connection.
How do you know? Like, I also struggle to wrap my head around the accuracy so it arrives in the right place. Do you still have control of it in terms of direction?
Yes. So Rosetta, the launch of Rosetta was delayed from the first possible launch window because of some issues with one of the outer panels. And then we launched a few days later, but that was actually the optimal time to launch. So we didn't need that much fuel. The fuel is hydrazine and an oxidizer. We didn't use that much fuel to get on the correct trajectory. That meant that we could fly by 2 asteroids. First asteroid Steins and then asteroid Lutetia. We also came back to the Earth 3 times.
Just a bit of a scenic detour on the way.
No, to gain energy, to become faster. You can do that with planet flybys. So 3 times Earth, 1 times Mars.
So is it the gravity of the planet will pull and speed it up? Is that what that is?
Yeah, it's a little bit more complicated. The planet pulls it, but if you then fly by, you will lose the energy again. It pulls you back. But because the planet moves itself, you can gain energy. I don't know if you felt it, the Earth got a little bit slower each time.
I didn't, actually. My time to work is approximately the same.
Yeah.
I didn't ask you, actually, where is the comet? Was it orbiting one of our planets?
No, the comet is orbiting the sun with a 6.5-year period. So the closest to the sun is just outside of the Earth orbit. It does not cross the Earth's orbit. And the farthest point from the sun is outside of Jupiter. It's on an ellipse.
What time window did you realistically have before you can't reach it anymore when you left?
Well, we would have had to wait another 6.5 years for it to return. Yeah, it was the backup. This comet was actually the backup, because the launch was foreseen on January 13, 2003. To Comet Virtanen would have been an easier name.
Yeah, that's for sure. Come on.
But then 1 month before our launch, there was a failure of an Ariane 5 with a commercial payload. And so they did an investigation of why it failed. Did this Ariane 5 in December 2002. and we were not allowed to launch. And the comet Virtanen did not wait. So we had to look for another comet. And that was Chury, and the launch was then more than a year later.
And during that time, like on a practical level as a project team, people must be coming and going. How was the atmosphere and the culture of the people working on this?
While we were building it, of course, there were a lot of engineers around. Software engineers, mechanical engineers, electronic engineers, and some scientists. But then with the launch, that changed. It was mostly PhD students doing the calibration of the model in Bern. And also not too much interaction with our co-investigators. And then came the two mission years. Of course, then it was very intense. We worked really 7 days a week, 24 hours, more or less.
And the mission years, that's between 2014 and 2016?
Yes,
Yeah.
yes. And you have to be really alert. You have to look at the data from your instrument. You have to see if it's still working nominally. You have to look at the science it provides. And you have to think of what you want to do next, because we could command. We had many modes. And depending on the mission phase, we use different modes. And then you have to archive everything and make it ready for your co-investigators and so on. And finally, for the public. All these data are public. You can look at them, you can evaluate them if you like.
Was there a lot of public interest at the time?
Yes, not for our data, because our data are just too complicated, but for the camera data. And there was quite some citizen science being done on camera pictures. You know, citizen science, these are people not involved, are probably not even physicists or space researcher. And they found a few very nice things in this huge data volume.
Is it just photos that were sent back in terms of the information which the public would enjoy seeing?
No, they also looked at our results, not at the data, because we gave them the results, the glycine you mentioned, but we have a lot more, of course. And the interest was quite high, also in our data.
The discovery of glycine, why was this such a important finding?
You know, when I started in 1982 on the Giotto mission, the goal of the Giotto mission was to prove that the comet really consists of water. So our instrument at that time had a mass range, the neutral mass spectrometer up to 32. Water is 18, 32 is O2, sulfur. So very, very simple molecules, because that was at that time the idea that the comet consists of. And then there was one instrument of Giotto which could not identify the molecules, but they could prove that there are molecules which are much, much heavier than the 32 we had. They could show that there are molecules at least to mass 100. And that's why we then built instruments which could go further. So the one instrument went to 140, mass 140, and then later to 180. And that's where you have the organics, the heavy organics. Mm-hmm. And well, glycine is just one of them. Mm. We have hundreds of organics. And many of them are important for prebiotic life. So
did you say so? Prebiotic?
Molecules which you need to create life. It's not life, but you need them to get the DNA in the end.
I was going to ask
you. They are on the comet.
That's what I was going to ask. What does this actually reveal about the universe, but it's one step closer to confirming that there is life out there somewhere.
Yes, there has to be life out there.
Did any of your existing assumptions get proved incorrect by what you found?
Yes, the complexity. We never expected the complexity of what's in the comet. Also, we found the xenon, and xenon is not like the terrestrial xenon, at least not the xenon we have in the Earth. So, but now we can explain why our terrestrial atmosphere is different from the Earth's mantle, so from the solid part of the Earth. In xenon, we have xenon in the atmosphere, we have xenon in the Earth's mantle, and they are not the same. They have different isotopes. That's different number of neutrons. And for more than 40 years, people were asking why. Why has the Earth a different xenon in the atmosphere? Now we know. You need 22% of cometary xenon, and you mix that with terrestrial xenon, and then you have our atmosphere, which is quite nice. So we know how many comets impacted the Earth. And that also tells us that our water does not come from comets.
I just try to wrap my head around how you can derive the water on Earth not coming from comets by the xenon made up in the atmosphere.
We know how much xenon we have in a comet. We know how much water we have in a comet. And we know how much xenon we have in the atmosphere. If 22% of the xenon in the atmosphere is cometary, that brings us about 1% of the terrestrial water. However, it brings more than today's biomass in organics.
What does that mean?
You know, biomass, that's all the organics which come from life, trees and grass and animals and whatever, bacteria. If you compute how much of this biomass we have on the Earth, and you compare it with, again, starting with xenon, we know how much xenon we have in comets, we know how much organics we have in comets, and you add that up, then you see that comets brought more than the biomass of organics. So it's very likely that life on Earth started because of comet impacts. You know, it's much easier to start life if you already start with some organics than if you have to start with just atoms.
And what is a method of confirming that a amino acid like glycine exists? How do you actually confirm what it is?
Well, glycine has a chemical formula consisting of CHNO. And that gives you the mass of glycine, which is 75 point something. And with the mass spectrometer, you measure the mass. And with our mass spectrometer, you really measure the absolute exact mass. And we found that there must be glycine because at exactly the position where you expect glycine, there was a peak. That's what you have the mass spectrometer for, you know.
And when the mission ended, so when finally the batteries ran out and it went cold, how did you feel?
It was a sad moment. You know, we had two options. One option would have been to go on, put it in hibernation again, as we did before, and 4 years later, wake it up again and continue measuring. If we would still have been around the comet, which we actually didn't really know. But at that time, we didn't have too much food left. And of course, if you navigate around the comet, you need some food because you have to actively steer the spacecraft. The comet is not heavy enough so that you can just work with gravity. You have to steer, you have to go forwards and back and around. And that needs some hydrogen.
Yeah, how are you steering? It's not a remote control, is it?
You send commands. So the problem was to know where we were relative to the comet. So they sent pictures down from Rosetta, and they compared it with pictures we already had from the comet, and from the pictures they determined where we were relative to the comet. And then they calculated how to correct the orbit in the next few days. So we did in ESTEC, in ESOC, in Darmstadt, they did it twice a week. Because you cannot just steer it like a car.
Yeah. Well, I'm trying to, and I guess if every
commands and hope the commands are correct.
And if every command takes 45 minutes or an hour to reach it, I suppose it's a very delicate process.
Yeah. And then you have thrusters, which you ignite with hydrogen and the oxidator, and that gives you a push in the right direction if you do it right.
How far is Rosetta from the comet at any given time once it reaches it and you're following it?
The closest before landing in the end, the closest was about 3 kilometers.
Okay.
But during the so-called perihelion, that's when you are closest to the sun, we had to retract to 300 kilometers because the comet got very active. And Rosetta, the attitude, how it looked, it got from pictures it took from the stars, compared these pictures to star maps, and then it knew how it looked. But close to perihelion, we had a lot of dust coming from the comet. And dust looks exactly like star.
Well,
it moves differently, but it was... We actually lost Rosetta for 3 days in March 2015 because of that. So we had to go away from the comet during perihelion.
And if it's very difficult to ensure it keeps up with the comet, how do you manage to land it?
The landing of Philae.
Yeah.
That was not that complicated.
No.
It was because the comet is not a sphere. You don't know how gravity works. You don't know the center of gravity of the comet. So the first months we spent finding out the gravitational field of the comet. But once you know that, you just release the lander at the right moment. It was released from 22 kilometers above the comet. It just fell along the gravity field and ended up on the comet exactly at the right spot. They did a good job in Darmstadt. Yes.
And luckily, it didn't sink and disappear.
Well, it hopped. Can you remember? It hopped. It landed at the right place, but the harpoons didn't work, so it went off again, and it hopped 3 times, and finally landed still on the comet, but not at the right position. It landed in winter. First, it landed in summer. The comet has summer and winter as the Earth. Summer hemisphere or hemiduck and the winter hemiduck.
So it landed in summer,
and then it hopped into the winter. And that's why the battery could not reload. So it measured for 60 hours, and then the battery was empty and no sun.
So summer and winter is the sunny side and the dark side of the comet. Is that what you mean?
Yes. Yeah, and that changes as of the Earth, because it has a rotation axis like the Earth. It's tilted. So it gets spring and summer and fall and winter. It's just very close to each other, 2 kilometers. Summer and winter hemisphere. But still, that's how it works, yeah.
That's amazing. I think I'm going to be processing this for the next week, trying to wrap my head around it. So, Kathrin, looking forward, what other achievements in space do you hope to see still in your lifetime?
Well, the next Comet mission is already being built. It's Comet Interceptor. It's going to be a small mission, much smaller than Rosetta, but it will again have a mass spectrometer from Bern, just a very small one, so it will not be able to find glycine. But it's a very nice mission. It will be launched in 29, most probably, maybe in 30. And it will go to the Lagrange point outside of the Earth. That's where the gravity of Earth and Sun is the same. They are equal at that point. A lot of spacecraft are out there observing the stars, and so James Webb is out there, and you can park your spacecraft there. And so the spacecraft will be parked for up to 3 years and waits for a brand new comet. A comet coming from the outer solar system, not a short period comet like Chury, which has been around the sun for already some years, but a brand new one which comes for the first time from these very far out places where it's really cold into the inner solar system. Once we find the comet, the spacecraft will intercept it like we did with Giotto.
So there's no defined period of time. It just sits there and waits until...
No, and we don't know which comet. So
Wow.
So when we launch, we probably won't know the comet we are going to. But that's the fun mission.
And so now you've been retired for some time, but still quite active at the University of Bern in space.
Yes, we are still analyzing data from Rosetta.
Amazing.
We are still working on the organics, currently on the organics with nitrogen, which are the most important one for prebiotic material. Because life has a lot of nitrogen. And that will keep us busy for another, I don't know.
And just it's amazing to me how what's that total time span from when it first started to when it ended? It must be more than 20 years.
I always claim it's 40 years. 10 years of planning, 10 years of construction, 10 years of flight. Well, here it was 12, and then 10 years of data analysis.
And you got into space by chance because it was an opportunity available. What can you derive from that to pass on to students today to figuring out what direction to take their career?
They just should stay open. You know, I didn't even do astronomy during my studies, but I was open to a lot of things in physics. I liked what I did for my PhD. It was super interesting. I liked physical chemistry in New York. And I didn't have a career goal to become a professor. That was just by chance.
Amazing.
And I think if you are open, you won't be disappointed. And you can grab your chances if they arrive.
Because I feel like...
And that's what I tell people.
Yeah.
Especially women, yeah.
And now it seems to be almost like the paradox of choice. There seems to be an endless options and what you can choose from, and it's almost overwhelming, feeling like you've got to pick the exact right thing from the beginning.
Yeah. And you know, physics is a very good subject. You can become everything. You can become Chancellor of Germany.
Indeed, yes.
You can become President of Mexico.
Oh, interesting.
Steinbaum. She's also a physicist. You can become director of a bank. You have a lot of opportunities. If you plan from the beginning that you want to become a professor in space research, I'm pretty sure you will be disappointed because the opportunity will not be there.
I see.
You know, there are not too many professors in space research, and you have to be at the right spot at the right time. And so just stay open.
All right. Well, Kathrin, thank you again. This has been a wonderful conversation. Thanks for listening. If you did enjoy the episode and you want to support me, it would mean a lot if you could rate the episode and follow the podcast on your favorite platform. It really helps the show grow and reach more people. I'll see you in the next episode.